Okay, now um, we're going to do something now for something completely different, and everybody should jump up and down and go, Monty Python. I wanted you to think about this. This is our characteristic polynomial, correct? So what I'm going to do is I'm going to create an operator that takes objects, squares them, whatever that means in this space. It's going to add on the object, and it's going to take 6 times the identity. So in other words, what I'm doing is I'm taking the characteristic polynomial and I'm creating an operator. So for example, if I take my matrix A and I put it in here, so I take the A, I square it, I add on the A, and 6 times the identity matrix. And if I do that, can I have a little drum roll, please? Guys, I can't hear the drum roll. You'll never guess what happens. Yeah, let me pull this all down. When we go through the arithmetic, if you just trust me, you end up with the 0 matrix. In other words, the matrix A satisfies the characteristic polynomial. The characteristic equation, excuse me. Now, what does this have to do with the e to the at? Remember, if we try to approach it as a series, we get into big trouble. So here's where what's called the Cayley-Hamilton theorem comes from. And it was just observed that when you put the matrix in there, and you put the matrix into your characteristic polynomial, you end up with, it satisfies its own polynomial. Well, when we do this, notice that what happened was the characteristic polynomial, let me back up, stopped at powers of 2. That's going to be of major importance. So if we have a square matrix, and the matrix could have real entries, complex entries, I'm going to have to look into quaternions. So you form your characteristic polynomial for your matrix A. Then it turns out that the Cayley-Hamilton theorem says that the matrix satisfies this. In other words, it equals 0. And so you've got some homework, 2 homework problems on that, plus actually calculating the things. Okay, so having a little problems with the focus there. There we go. Okay, so we're not going to prove this. You may or may not have seen this. I don't know if you've seen the Cayley-Hamilton theorem in linear algebra, but you probably, if you did, you probably did not see the proof. This is more at a graduate level. So if I let A be an n by n matrix, it can be shown with a lot of effort that the infinite, remember when we tried to go through this as a series, we had an infinite number of terms. Well, it turns out that the matrix, the exponential matrix, actually stops at 1 term less than the order of, or the degree of your matrix. And so what this is saying is that, so if A is a 2 by 2, this stops at, what would it be? These two guys. If your matrix is a 3 by 3, it would stop at here. That is a tremendous saving, because what happened was, this thing was, you had an infinite number of terms, and this Cayley-Hamilton theorem says you could just stop it at here. But the problem is you have to figure out what these coefficients are. Okay? So instead of working, this is a ooh-ah moment. Instead of having this as an infinite series, you can actually stop it at a finite number of terms. So if this is a 3 by 3, you stop it at this 2, which is a really, really big savings in terms. So the alphas here, the coefficients, are going to be functions of the numbers and t. And so here I've just noted if the the matrix A is a 2 by 2, then you just stop it right here. There are only two unknowns, the alpha 1 and the alpha naught. If you have a 3 by 3, you stop it at the squared terms. And the so what we have to do is we have to define this a polynomial, if you will, in lambda. Obviously, lambdas are going to be the eigenvalues. So what we're doing is we're forming this polynomial, like for example here, or if it's a 2 by 2, this one, which we'll be looking at. And so if I form this is not the characteristic polynomial, okay? This is something else. We don't know what the alpha. We'll talk about how you get the alphas. And it turns out that if the lambda is an eigenvalue, then e to the lambda I is equal to this thing evaluated at lambda I t. And what we're going to do is so if we have two eigenvalues, we're going to have two equations. And so what's going to happen is you're going to have two equations because you don't know what the alpha 1 and the alpha naught is. Let's take an example. So suppose I tell you that the matrix A is a 2 by 2, 1, 1, 9, 1. And we do the following. E to the AT, that's this guy, is going to be A times T. So the degree, so this is a 2 by 2, which means we stop it at what? N equals 1. So the question here is, what is my alpha naught and what is my alpha 1? So I have two unknowns. What that means is I'm going to have two equations. So let's do the following. This e to this t can be written as this, so we're just going to expand out. I take my matrix, I take my identity. We don't know what alpha naught is or alpha 1. So just put them, expand out, and we end up with sorry about the wires all in the way. So it turns out that this 2 by 2 matrix exponential can be written as a 2 by 2 where there are two unknowns, alpha naught and alpha 1. And how do we find those? So the first thing I've got to do is I've got to figure out what the eigenvalues are, and we could do this using Mathematica. That's fairly trivial. So we have one eigenvalue 4. So what this is saying is e to the 4t has to be r. It's not the characteristic polynomial. So I put in a 4t for my lambda plus alpha naught. Notice I have this equals this. That's one equation. I have two unknowns. I need another equation. That's where the lambda equals -2 is going to come from. So if we take the lambda 2, e to the -2t is equal to r minus 2t. So you just put in a what? -2t for your lambda stuff. Now you have the two equations in the two, you have this equation and you have this equation and the unknowns alpha naught and alpha 1. So we have this equation and we have this equation, which we now have to solve for alpha naught and alpha 1. So it turns out, now you're going to be, obviously you're going to be doing some homework to do this, and I show you how to do it. You're going to use the solve command in Mathematica. So we're going to solve a system of equations for the alpha naught and the alpha 1. And it turns out, so you just use your solve command, and you can get what your alpha naught is and your alpha 1, so you can substitute it into your, so this matrix exponential now just becomes a 2 by 2 matrix, which is really nice. So Mathematica, here we go. So hopefully you could read this on your lecture notes. So the first thing I did was I created the matrix A. Then, because I'm such a horrible typist, I want to check to see that I've actually typed that in correctly. Not incorrectly, but I typed it correctly. So then I notice I don't need the eigenvectors for this. All I need is the eigenvalues. So it turns out there's two of them, 4 and -2. We create the identity matrix, because remember I'm going to have characteristic polynomial. I want to check things. So here's my, I'm going to create my, so this is my alpha 1 times t times my, to express, so this is my alpha naught alpha 1 equation. We'll put it in matrix form just to check. And then we do our transformation. So I say, so I had e to the 4t is equal to this, remember that? And e to the -2t was equal to that. So you have to use double equals. And I'm solving for that. And I do flatten. What that does is it removes excess curly braces, that's all. And so I now know what alpha naught is and alpha 1. Now this little symbol here is a transformation. When you go to type in transformations, it has to go like this, a minus sign, then a greater than, less than, whatever you want to call it. And then what Mathematica comes back with is this arrow that you see right here. That's a transformation. So I'm going to keep that, and I'm going to take my matrix exponential, which is back over here. I didn't know what the alpha 1s or the alpha naughts were. So then I take, this means replace, let me put that in there, replace repeated. And what that means is it takes every instance of alpha naught, replaces it with this, and every instance of alpha 1 replaces it with this, and so you get this mess. And I put it together, and so this becomes my excuse me, this becomes my matrix exponential. I'm just going to call it C11, C12, C21, C22. So now I have what my matrix exponential is. And if you compare that with what we got in previous, everything works out. Okay, so you could check that. If the eigen so I checked that, C11, C12, C21. So you can go through checking that. That's just some busy work. Now it turns out that if you have repeated eigenvalues, I want you to think back in ordinary differential equations. You remember when you had something going on with repeated stuff, you have to take derivatives. So if you have one of the eigenvalues is repeated, then you have one equation, then you have another one. If you had 3 of these, you'd have a second derivative. You had 4 repeated, etc. So let's do the following, because it takes longer and longer to upload. I'm going to leave it there.